And next we have Sarah tell us when reionization ended.
Hi, can you hear me?
Yep.
Okay.
Please.
Right. Hi, everyone, and thanks for giving me a talk at this great conference. Today, I'd like to present some new measurements at the end of reionization. We've heard quite a bit about reionization yesterday already. Reionization is a phase transition by which the hydrogen in the intergalactic medium goes from being completely neutral at high redshift to homogeneously ionized around redshift 5 and then all the way to the present day. We can probe the end stages of reionizations quite conveniently by using high redshift quasars as skewers, as shown here. So the continuum emission of the quasar is absorbed by the foreground IGM. And you can see that at redshift 5 or so, there's a lot of transmission left in the last remnants of the Lyman-alpha forest. But by the time we get to redshift 6, there is not much transmission left at all. Interesting things are happening in this intermediate region when we observe too much scatter between quasar sightlines at the same redshift. This was illustrated dramatically by this pair of sightlines, the black one here showing a large amount of transmission and the red one being completely absorbed, even though they're at the same redshift range, 5.6 to 5.8. So in other words, there is an extreme contrast in optical depth of Lyman-alpha, even at fixed redshift. So it has been shown that this extreme scatter in optical depth cannot be explained in a homogeneously ionized universe by accounting for density fluctuations, or even when you include temperature fluctuations. So instead, the models that can reproduce this observation involve a very late end to reionization. So where these opaque absorbed troughs actually contain gas that is 10% neutral or more, and or a short mean free path of ionizing photons inside of ionized regions. So the physics at the end stages of reionizations have been shown to have consequences for both the 21 centimeter signal, as well as the possible sources of reionization and their properties. So of course, we'd like to understand a bit better what's going on. And the specific question I wanted to answer, and we now can, thanks to the XQR30 sample, is when does this optical depth scatter end? So in other words, at what redshift does the universe fall in line with being homogeneously ionized and the phase transition is complete? So to answer this, we use the XQR30 sample that Valentina just presented, which are shown here. Because we are fighting cosmic variance, we do have to supplement it with ever so slightly inferior spectra from Extruder and ESI. But the resulting sample is still one of the largest and represents a leap in data quality by a factor 2 to 4, depending on how you want to count it. Okay, so as always, when you want to push a measurement to new levels of precision, you're going to run into a new type of systematics. So of course, the old ones we already knew, like accounting for the effect of the quasars in the background or overlap with the Lyman beta forest, the exclusion of galactic medium from the measurement, which we can now do to a very high accuracy, thanks to the metal identification in XQR30, as well as new systematics. For example, in the sample, we were very careful to only use 2 spectrographs and make sure there were no differences in data reduction or instrumentation between the two, which we checked carefully, as well as fixing more arcane effects that were introducing covariance as fixed redshift. One systematic I'd like to spend a minute on is this issue of continuum reconstruction. So this is a quasar at redshift 2, and it's Lyman-alpha forest. And as you can see at redshift 2, you can kind of guess or where the intrinsic continuum of the quasar is, just shown here in blue. But at high redshift, the Lyman-alpha forest is almost completely absorbed. So instead, we have to predict or reconstruct where this continuum is based on the features that we do see. These are 2 methods that were used in past studies to measure the Lyman-alpha optical depth at high redshift. It's PCA and Paolo in purple and green. And not only they're not very accurate, but you can also see they actually introduce complicated wavelength-dependent systematic biases that were underestimated before. So in this large comparative study published earlier this year, we tested 8 state-of-the-art reconstruction methods and converged on the one of the best performance, which is a version of a modern log PCA, shown here in red. And this plot shows the residuals of our reconstructions in a low redshift test on about 5,000 EBOS quasars. And you can see there are no wavelength-dependent effects in the predictions. And for the first time, we have a firm handle on what exactly the empirical uncertainty is from low redshift. And it turns out correcting this systematic made the largest difference in addition to data quality. Okay, so here are some results. This is the measurements of the mean optical depth of Lyman-alpha measured in chunks of 50 co-moving megaparsecs towards our 67 sightlines. You can see that at low redshift, the distribution of measurements is, even by eye, roughly Gaussian. And each individual measurement is much more accurate than the distribution it's sampling, which is why we need a large number of them. By the time we get to redshift 5.6, you can see this extreme contrast between extremely transmissive and opaque sightlines. And some sightlines remain transparent even at the highest redshifts, although only a few. The evolution of the mean flux is extremely smooth. This plot shows the evolution of the mean flux in flux space. Again, you can see it's extremely linear from redshift 4.9 to 5.6, as shown in red. We are in vague, in fairly good agreement with past literature samples, and we have been able to track down almost all of these disagreements to higher data quality and the removal of these continuum reconstruction systematics. So hopefully, a very nice relation for models to calibrate to. Okay, so what about the distributions at fixed redshift? These distributions in black are the new ones showing the distribution of optical depths compared to the previously state-of-the-art results in red. And the data quality and the removal of systematics have had a comparable effect of making everything smoother. So you can see the black distributions have less spurious features in them. We have better exclusion of galactic material. And the removal of systematics also introduced some systematic shifts in the data before. You can also see that the fraction of non-detections is much lower, especially at redshift 5.8, because our observations are deeper now, thanks to XQR30. So actually, the number of non-detections has shrunk by a factor of 3, although not at redshift 5, where most sightlines are 6, where most of them are still saturated. Okay, so now we can answer the question I asked at the beginning. When down to what redshift do we see excess scatter in the Lyman-alpha optical depth distributions? So to answer this, we compared our observations divided in bins of 0.1 in redshift to homogeneous UVB models. I'm going to show results from the NIC simulation, but we also cross-checked with Sherwood. Both of them use a homogeneous Hartle-Medow UVB. And wanted to check that changing the box size or the code or the number of snapshots was not having much of an effect, as I'll show briefly at the end. All right, so for our comparison, we use a fully forward modeled maximum likelihood approach in which for each measured optical depth tau along a sightline, we post-process the entire simulation to the optical specificities of that sightline, including any masking, wavelength sampling, flux uncertainties, and continuum uncertainties. We compare that to observations to get the probability of measuring this tau in this sightline. Then we aggregate these probabilities into a data likelihood. To interpret this likelihood, we then create 10,000 mock data sets with the same size and all observational specs as the observations. We get a distribution of simulated likelihoods, and then by comparing those, we can deduce the probability of our full data set of observations instead of having a high-level summary statistic. These are the distribution I'm showing at the bottom. These are the distribution of simulated likelihoods in 10,000 mocks in blue, and a KDE as the blue curve. And the black line is the likelihood of the observations. At redshift 5, 5.1, and 5.2. While the top panels are the observed distribution functions in black and the 1 and 2 bootstrap uncertainties from the simulations in blue. And you can see that at these low redshifts, where our distributions are actually exactly as expected from the homogeneous UVB models, they fall within the central sigma. And this is a great sign because it means we're not missing any crucial systematics that we haven't post-processed the simulations with. So no signs of excess scatter at these low redshifts. we start to see tension at redshift 5.3, where our data has slightly too much width to it. It falls in the tail of what you would expect randomly. And then by the time we get to redshift 5.4, the observed data sets are strongly excluded by the models at our sampling limit of 4 sigma, as well as at redshift 5.5. And of course, at all redshifts above 5.5, the existence of these extremely opaque troughs has already disproven homogeneous UVB models, but you can also see that the entire distribution shape is far too broad. All right. So in summary, this plot shows the tension between the homogeneous UVB models and our observations as a function of redshift, or Sherwood and Nix as the 2 colors. And basically, homogeneous UVB models fit extremely well up to redshift 5.2, which is remarkable considering that Sherwood actually fits the Lyman-alpha forest all the way down to redshift 2 extremely well. And divergences from these simple homogeneous UVB models happens fairly quickly by redshift 5.4. So we have not investigated possible causes yet of this, but it is broadly consistent with a late end of reionization. Because if the last neutral patches of gas are ionized around redshift 5.6, then you would expect temperature density fluctuations to persist for a bit longer because of the different timing of reionization. But other explanations could be possible, like late persisting fluctuations in other physical parameters. All right, so in conclusion, thanks to the XQR30 sample, we have really pushed the study of the high Z Lyman-alpha transmission to a new precision regime. And from the point of view of the mean Lyman-alpha optical depth, the transition to a homogeneously ionized IgM is complete at redshift 5.3. Thank you.
Thank you for a great talk. So let's wait for the questions on Slack. Or waiting, let me ask a question. So what is the neutral fraction that you measured at redshift 5.3 when you said the tension sort of started?
Right, so this is the neutral fraction measurements up to redshift 5.3. It's a bit low. So at redshift 5.4 and above, we only give those as limits because the calculation of the neutral fraction relies on the model comparison. And you can't assume that the homogeneous UVB models are correct at these high redshifts. And we think that's maybe why this 5.3 point is a bit low. It's at around 3, 10 to the minus 5.
Okay, thank you.
Yeah, so give people a couple of more minutes to ask questions. But I had sort of a question about the size of these regions. I seem to remember when George Becker I was talking to George Becker, he was talking about how these troughs actually extended for significantly larger than 100 megaparsecs, some of them. So I'm just wondering do you think the simulations might even the your large volume simulation might be missing some of these very largest troughs that might be giving rise to some of these most extreme deviations?
Oh, for sure. I mean, even larger boxes at redshifts more than 5.5 cannot reproduce the troughs.
I see.
At low redshift, actually, our results agree very well with the ones that Youngda presented yesterday, because they don't find any troughs more than 30 megaparsecs below 5.3. They just seem to end.
Okay.
But in our measurements, we actually checked that if we exclude all troughs at redshift 5.4, we are still in strong disagreement. So this is this plot here. At redshift 5.4, we actually our measurement doesn't depend on the existence of these troughs, because this is showing them just cut out. And it's really the variance of the measurements of the entire distribution.
We have one question from Brandt. How robust are your conclusions about the homogeneous UVB models to photoionization and photoheating history? that you adopt, specifically Hartman Dow 2012. Can simulations with other photoionization or photoheating histories explain your data?
At 5.6, they can't, because we already know this from the long troughs comparisons. We haven't checked if at redshift 5.4, just changing the slope of the temperature density relation would make a difference, but we suspect it will not. You have to have scatter between individual locations, and not just an adjustment of the whole.
Thanks.
All right, I think we should move to the next talk. So thank you, Sarah, again.